All right, calculus students, a message from Grace Jersvik. She thinks that sophomores are better than seniors. That's her quote as I'm recording this during 8th hour because I forgot to during 5th hour. I'm sorry, y'all, especially Claire. I told you I'd do this for you, so here we go. So you guys can continue to work, but this is going to take me about 15 minutes to get through. So anyway, today we want to cover a topic on Newton's method, and really the problem statement is as follows. The problem statement is, how do we find solutions to higher order polynomials, especially those that are irrational? So if we have a function that has an irrational solution, how do we find it? And again, you guys would go to your calculator. Well, we don't have a calculator. We got to try a different method. To even further this point, let's suppose that you had something of the form ax squared plus bx plus c equals 0. Well, you know full well that x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. We have the quadratic formula to be able to use for that. And the fact is that we also know how to solve cubics, and we also know how to solve quartics. It is very long and painful, and we would not like to use that. After we have cubics and quartics, we don't know how to solve the rest. We're left to other methods. So back when Newton had developed calculus, he had a very quick way to be able to find solutions, especially to those things that were not rational. Now, I want to look at this example. What if we want to find the square root of 5 to 4 decimal places? And I think that people would agree that the function f of x is equal to x squared minus 5 has solutions at plus or minus the square root of 5. And if I draw that graph like so, it would cross right at the square root of 5. Now the square root of 5 sits between two numbers. It sits between the number 2 and the number 3. And here's the idea. Newton realized that if we were to find the function evaluated at 3 and then draw a line tangent to that function at that location, the x-intercept of the tangent was a good estimate. As a matter of fact, he could take his new guess and find that spot again and draw another tangent line, and you can see how close that x-intercept lies right to the actual solution. And he would do this to approximate what the actual value of square root of 5 was. And so let's actually do this. I chose my initial guess to be 3. That would mean that the point on my line would be 3, and whatever I get when I plug 3 back into my function, 3 squared is 9 minus 5 is 4. So the point on my line is 3, 4. And if you want to find the slope of that tangent line, you need to find the derivative of the function, which in this case is equal to 2x. So the slope at 3 would be f prime of 3, which is 6. So 6 is the slope. Using this, we can be able to come up with a better guess. Again, if you look at my drawing that I created, 3 was a guess. That was my guess. In order to get a better guess, I can find the equation of the tangent line and find out where it crosses the x-axis. So the idea is, what is that x-intercept of the tangent line? X-intercepts occur where y is equal to 0. We're going to find that, okay? So, equation for the line, I'm going to use my point slope formula, which says y minus y sub 1 is equal to m times x minus x sub 1. I have all the information I need. Y minus my y value is 4 equals my slope, which is 6, times x minus x sub 1, or x minus 3. So there we have it. That's the equation for the line. Where does it cross the x-axis? It crosses the x-axis wherever y is equal to 0. If I plug in 0, I end up with this. Negative 4 equals 6 times x minus 3. If I want to solve for x, divide both sides by 6. Negative 4 over 6 is equal to x minus 3. Add my 3 to both sides. 3 minus 4 over 6 is equal to x. Now, I haven't reduced 4 6 for a specific purpose. But if you take 3 minus 4 over 6, you would get 2.3 repeating, or 2 1/3. And that would be the new guess of which I would calculate, 2.3 repeating. Now, if we just see how that works out, if you would take your calculator and you would say, what is 3 squared? That's 9. So 3 wasn't a very good guess for the square root of 5. But if you try 2.33 and square it, you come up with a really good approximation, 5.44. If we then made a new guess of 2.33, we would come up with even a better approximation. So Newton would do this over and over again, and he would come up with, ultimately, the correct solution. Well, he wouldn't do this, though, each time. He wrote for himself a little bit more of a formula that works out, and we're going to do that as well. First thing I must identify is my guess. And we're going to make an initial guess of x sub 1. After we guess x sub 1, we are going to use our point on our line. Our x value would be 1, and our y value would be whatever we get when we plug it back into the original function. My slope is equal to that guess evaluated at the derivative. If you look, we took 3, we plugged in our function to get 4, and we plugged 3 into our derivative to get 6. So f prime of x minus, or x sub 1 is equal to my slope. And now I write my formula. Y equals my y sub 1 value. Y minus y sub 1 is f of x sub 1 equals m, which is f prime of x, times x minus x sub 1. Again, our goal is to find the x-intercept. We want to solve for x. The x-intercept occurs where y is equal to 0. So I set y equal to 0. And I get negative f of x sub 1 equals f prime of x times x minus x sub 1. If I divide both sides now by f prime of x, I get negative f of x over f prime of x is equal to x minus x sub 1. Now if I add an x sub 1 to both sides, I get the resulting formula. X sub 1 minus f of x sub 1. Oh, forgot some notation there, sorry. Over f prime of x sub 1 is equal to x, and that represents my new guess. Spelled guess wrong, I did during the class as well. So, what does that all mean? Okay, if you look, if we would call our new guess x sub n plus 1, that's our new guess, our better, more educated guess, that would be equal to your original guess, or your previous guess, minus the function evaluated at your guess divided by the derivative evaluated at your guess. And using that formula, we could come up with a really good estimation for, say, the square root of 5. Now, on the back side of the sheet, I'm actually going to try coming up with, it didn't print off here for whatever reason, but I'm going to try to approximate the square root of 7. In order to do that, I will use the function f of x is equal to x squared minus 7, because it has a root at square root of 7. And I'm also going to need f prime of x, which is 2x. And the reason why I use those two is because, again, Newton's method says that x sub n plus 1 is equal to x sub n minus f prime of x sub n over, f of x sub n over f prime of x sub n. So that's what Newton's method says. So I need the function, I need the derivative. I have both. Well, the square root of 7 lies somewhere between 2 and 3. I'm going to guess 3. 3 squared is 9. That's fairly close to 7. Let's see if we can approximate that value here. Newton's method says x sub n plus 1 is equal to my guess, which is 3, minus my function evaluated at 3. The function evaluated at 3 is 3 squared, which is 9, minus 7, which is 2, divided by my derivative evaluated at my guess. The derivative evaluated at 3 is 6. And 3 minus 2 over 6 is equal to 2.6 repeating. So 2.6 repeating is my new guess. Let's just try to see how close 2.6 repeating is to, if we were to square that, how close do we actually come out to 7? Well, 7.111. That's really close. That's really close. If we want to come closer, we repeat the process, but we plug in 2.6 repeating. So my new guess will be, whatever I get when I plug in 2.6 repeating minus my function evaluated at 2.6 repeating. Well, let's try that. 2.6 repeating squared minus 7. And I get about like 0.1 repeating, looks like. So 0.11111 over, and on the bottom we would have 2.6 times 2. So the that new guess evaluated at 2. So 2 times 2.666 repeating. Enter is 5.3 repeating. So 5.333 repeating. Now notice we're using our calculator to even help us do this more quickly. Newton would do this all by hand. And yes, it would take him longer, but he came out with amazingly accurate answers. So if I would take 2.6 repeating minus parentheses 0.11111 divided by 5.33333, close my parenthesis, I get 2.6458. 2.64583. 2.64583. And if you would take that 2.64583 and square it, you can see how close you actually come to 7, 7.0004. So in fact, 2.64583 is a really good estimate. If you wanted to actually find a better one, you would then say my new guess is equal to 2.64583 minus the function evaluated at 2.64583 divided by the derivative evaluated at 2.64583. And if you do that, it doesn't change much. You come up with 2.6457. And if you take 2.6457 and you square that, you can see 6.9997. You can see you end up coming up with values that are very, very close to 7. So this thing is working its way out. You can see a good approximation for the square root of 7. We continue the rest on Monday. But that's the idea behind using Newton's method, very useful in finding solutions to irrational numbers, or I'm sorry, approximately irrational numbers, but also finding roots to higher degree polynomials, which is what we will pick up with on Monday. Have a great weekend.